I am Chantal Roth. I am a software and algorithms developer at Thermo Fisher Scientific. The field of artificial intelligence and machine learning is not only of great interest to me personally, but it is also an important developmental focus here at Thermo Fisher Scientific. And so I'm very excited to introduce our next speaker, Dr. Mark Barash. Dr. Mark Barash is an associate professor and co-director of the Forensic Science program at San Jose State University. With over 2 decades in the field, including 10 years of operational experience, he has significantly contributed to the field of forensic DNA analysis in teaching, research, and casework. Dr. Barash's research interests span multidisciplinary areas, particularly focusing on employing machine learning and bioinformatics to predict physical characteristics from DNA samples, showcasing the powerful intersection of artificial intelligence and forensic genetics. He will be talking about unlocking justice, the AI revolution in forensic science.
Good day, everyone, and thanks to Thermo Fisher Scientific for the invitation to give a talk at HIDS 2024. My name is Mark Barash, and I'm a professor and forensic science program coordinator at San Jose State University. In this talk, I would like to introduce you to the topic of artificial intelligence and machine learning to make sure that you are aware of the AI revolution already happening in forensic science and particularly in the field of forensic DNA analysis. Imagine walking into a room where a cold case left unsolved for decades is laid out on a table. The evidence is there: fingerprints, DNA profiles, photos of the scene. But for years, this puzzle remained unsolved. Now, imagine we have a new key to unlock this mystery, a key forged from the advanced algorithms of artificial intelligence. Envisage a future where forensic science reveals the story behind every trace found at a crime scene. This future is much closer than you might think. AI and machine learning are not just revolutionizing the way we live, work, or think. They are transforming the very fabric of forensic science. Today, I'm going to take you on a quick journey into the heart of this transformation. But first things first. AI is a distinct branch of computer science and engineering that focuses on creating technologies capable of predictive analysis by learning and executing cognitive tasks that typically require human intelligence. These tasks include decision-making, visual perception, language understanding, and more. At the same time, machine learning is a range of powerful computational algorithms representing a subfield of artificial intelligence capable of generating predictive models via intelligent, autonomous analysis of relatively large and often unstructured data. Machine learning algorithms are designed to train a computer program how to learn from experience and improve over time, in a way similar to how a child learns new skills from their everyday experience. AI's impact spans across sectors, penetrating almost every aspect of our lives, and forensic science is no exception. Like the private sector, many federal agencies are expressing interest and investing in AI-enabled technologies that may be capable of optimizing resources and expanding capabilities across many industries. For forensic science service providers, AI-enabled technologies represent a significant opportunity to improve the way they identify, analyze, and reach conclusions on forensic evidence. However, its integration here is nascent, often limited by the gap between forensic experts' acquaintance with machine learning capabilities. Yet, the potential is immense, from enhancing evidence analysis to unlocking cold cases. So, let's first demystify what machine learning really is. Imagine training a dog. You reward it for correct actions. It learns. This is similar to supervised learning, where an algorithm learns from labeled data, often called training data. Unsupervised learning, on the other hand, is like observing birds in nature to understand their behaviors without professional guidance. Semi-supervised learning mixes both, using a little labeled data to guide the learning from a larger pool of unlabeled data. And finally, Reinforcement learning is akin to teaching a child to ride a bike, learning from trial and error. Now, most AI systems are machine learning based, where machine learning algorithms use inferences derived from data to find correlations and patterns that allow them to make predictions about similar new data. To better understand the basic principles behind different methods of machine learning, let's think of machine learning as a versatile chef in a kitchen full of ingredients, our data, where each dish represents a task or a problem. Obviously, our machine learning chef would require a different cooking technique for each dish. So, classification problem is like sorting ingredients into bins, fruits into one and vegetables in another. An example of classification approach would be distinguishing handwriting styles, where the dataset for classification includes examples of handwriting and the prediction categories are individual letters or words. Regression predicts how long it takes to bake a cake based on past cake baking experiences. An example is an estimation of the post-mortem interval by analyzing decomposition rates based on correlations found in previously collected data. Clustering aims to group similar things together, like sweet fruits or savory spices. And a forensic example would be clustering hair samples based on morphological features. Dimensionality reduction simplifies recipes by removing unnecessary steps while keeping the dish delicious. In the area of forensic analysis, dimensionality reduction is often applied in order to predict the biogeographical ancestry of a person. So here, highly dimensional data can vary from a few dozen single nucleotide polymorphisms to over 1 million SNPs per sample. These data are reduced to 2 or 3 dimensions, which explain most of the variance in the data and can then be analyzed or visualized much easier. At the same opportunity, I want to mention a few advanced machine learning approaches to these problems and explain them using highly specialized MasterChef analogy. So, natural language processing approach can be visualized as a chef that understands and follows a recipe written in any language. Generative models is a highly experienced chef that invents new recipes after tasting and studying countless dishes. These master chefs isn't just copying, they are innovating by introducing highly creative dishes that could easily get a Michelin star. We'll get back to these generative models shortly. Now, let's see how AI is already transforming the landscape of forensic investigations. In the realm of forensic science disciplines, machine learning algorithms can be trained for automated identification, classification, and verification of fingerprints, shoe prints, and bullet striations. Additionally, speech recognition algorithms can transcribe and analyze audio recordings, identifying speakers or detecting keywords, while video analysis algorithms can automatically recognize faces, track movements, perform gait analysis, and even analyze the behavior of individuals in a footage. To perform the predictive analysis of this complex data, machine learning models must be trained on very large datasets to accurately recognize unique features and patterns, enabling more objective analysis of impression and pattern evidence based on quantitative and qualitative data. While tools like ChatGPT showcase AI's utility in summarizing complex information, and generative models and natural language processing offer new ways to approach forensic evidence, the true potential lies in AI's augmenting human investigators' effort. AI can essentially be a part of the investigative team, collaborating with human partners in a brainstorming process, helping to uncover new leads and perspectives that might have been overlooked. AI algorithms can extract comprehensive information from various types of forensic evidence by analyzing multidimensional data points and finding hidden patterns linking between traces, crime scenes, and people. Notably, the application of these tools offers an opportunity not to only arrive at a decision as to whether the crime scene evidence matches the references, but also to quantify the similarity between items and calculate the likelihood of that match being true. This would improve standardization and reduce the inherent subjectivity of forensic pattern analysis. And perhaps most importantly, this exemplifies a truly holistic approach to forensic evidence, a critical missing link that has been highlighted in numerous studies. I know what you're thinking. No, AI is not going to totally replace human investigators. AI can indeed process and analyze vast amounts of data at speeds unattainable by humans. At the same time, human investigators bring critical thinking, intuition, creativity, and investigative experience that AI cannot replicate yet. Therefore, the ideal approach is synergetic, where AI provides insights and suggestions based on data analysis, while human investigators can then delve deeper into these leads, using their expertise to verify, expand, and act upon the AI-generated insights. In fact, I'm 100% sure that in a couple of years, we'll see most law enforcement agencies making their own generative AI systems capable of consolidating big data from hundreds of thousands of criminal cases, allowing the AI detective to find hidden patterns linking multiple crime scenes and people. Kind of a 24/7 personal Sherlock Holmes or Hercule Poirot, or whoever's your favorite detective. No doubt, this approach will revolutionize the investigation process. At the same time, it is important to remember that even though AI helps reveal hidden patterns in data, it does not ultimately reveal why these data may be related in a way people can easily understand. We'll get back to these problems shortly. Now, let's dive into the core of our discussion: machine learning applications in forensic DNA analysis. So, current applications of machine learning can be arbitrarily divided into several areas. Applications related to human identification, applications related to forensic intelligence, and those related to increasing the evidential value of biological evidence. Now, as you know, the contemporary process of STR genotyping and data interpretation consists of numerous steps, while the complexity of separating the alleles from background noise and artifacts is essentially the basic problem in forensic DNA analysis. Currently, the process of STR genotyping is carried out semi-automatically using dedicated expert software such as GeneMapper. This software separates allele peaks from noise and artifacts with the help of built-in algorithms and utilizes a number of validated thresholds, resulting in the detection and removal of stutters, pull-ups, and other artifacts. The resulting DNA profile can be compared with a reference profile or further analyzed by probabilistic genotyping software. However, the overall process is tedious and prone to significant variability in interpreting complex DNA mixtures. Furthermore, with the rapid implementation of massively parallel sequencing, the generated bioinformatic data becomes even more complex, requiring trained personnel and significant resources. The problem of accurately classifying such a diverse range of variables might be better addressed by a more sophisticated machine learning approach, deep learning. Deep learning methods utilize variations of a hierarchical organization of artificial neurons with connections to other neurons, similar to the brain structure. These neurons pass a signal to other neurons based on received input, a process that can be repeated multiple times, which ultimately creates a complex network capable of intuitive learning, an artificial neural network, ANN. Using the culinary world analogy again, think of deep learning as a master chef who trains a team of specialized sous chefs, our neural networks, to handle complex and layered recipes, our data. So each sous chef focuses on a specific task like chopping or baking, learning from every dish they make. As dishes pass through the kitchen, each chef adds their expertise, resulting in a sophisticated final dish. Similarly, in the artificial neural network, each layer of neurons performs transformations using weights, biases, and activation functions. This process continues until the data reaches the output layer, where final predictions are generated. Another puzzle well suited for machine learning approach is the interpretation of complex DNA mixtures, especially if one or more of the contributors is represented by a low-level portion of that mixture and if the DNA molecules are degraded. In such a common forensic situation, a true allele can be confused with various artifacts. All these variables may be influencing one of the key parameters in DNA mixture interpretation, estimating the number of contributors. Now, machine learning offers the tools to piece these puzzles together, distinguishing between the true alleles and artifacts, resulting in identifying even low-level individual contributors with unprecedented accuracy. First, instead of using static analytical and stochastic thresholds, the machine learning algorithms do this by utilizing either a dynamic threshold or refrain from applying any thresholds. At the same time, they can efficiently recognize various artifacts and remove them. This way, machine learning methods can utilize all the available information in the raw EPG or sequencing data to learn and make informed predictions, maximizing the information obtained from the DNA evidence. One such example is PACE. This machine learning software has demonstrated remarkable accuracy in predicting the number of contributors for single-source samples and mixtures with up to 4 contributors. Furthermore, by combining various methods of machine learning, it is possible to build even more powerful models that could be used to analyze a variety of very complex incoming information. An example of such an approach is generative models, which I mentioned earlier. Generative models often incorporate layered networks that utilize multiple levels of non-linear data processing to extract and transform features of interest. One popular example is generative adversarial networks, GANs. The key innovation behind GANs is their two-network architecture consisting of a generator and discriminator networks. The generator creates synthetic data, and the discriminator evaluates whether the data is real or fake, leading to a competitive training process where the generator becomes increasingly skilled at producing highly realistic data. One of the most intriguing applications of ANNs and GANs is the prediction of an individual's visual appearance from a DNA sample, producing investigative leads wherein traditional means are unsuccessful. This task is exceptionally challenging due to relatively limited knowledge of the underlying genetic and epigenetic architecture of these complex visible traits. Therefore, GANs models are expected to lead to more accurate predictions of these traits, especially facial appearance, as demonstrated by a few recent proof-of-concept studies. Machine learning also comes to the rescue by imputing missing genotypes in partial DNA profiles. This imputation approach may be especially helpful in forensic genetic genealogy because this process often involves generating and interpreting SNP data and estimating genealogical relationships in circumstances where the resulting SNP profile often contains numerous errors or gaps. Moving to the forensic microbiology area, machine learning can help analyze the complex microbiome formed on a decomposing body to estimate the post-mortem interval more accurately. Additionally, machine learning algorithms can now confirm the biological tissue source and estimate biological age from epigenetic data, producing valuable forensic intelligence. This information would add layers of context to the evidence and help to produce insights into how DNA was deposited on the object, assisting with activity-level reporting. And finally, AI can be utilized in forensic labs to streamline the genotyping pipeline logistics and reduce the overall cost and time of analysis by incorporating automatic, intelligent triaging step, helping the analyst to decide which samples are worth processing further and which would most likely be a waste of resources. So by now, I'm sure you can agree that integration of AI machine learning clearly represents a paradigm shift from traditional forensic methods. It has the potential to revolutionize the analysis of forensic traces, streamlining the process and, even more importantly, making it more accurate and sanitized. However, as with any powerful tool, there are several limitations related to AI implementation that the forensic, law enforcement, and legal communities should take into consideration. By their nature, forensic applications demand unparalleled accuracy and reproducibility, areas where current AI tools, despite their potential, present significant challenges. A core issue with these technologies is their black box nature. This complexity possesses a particular challenge for non-computer science specialists, legal professionals, and jury. Moreover, the data used to train these tools often encapsulates another layer of complication. Issues such as non-representative datasets can introduce systemic biases, skewing results and potentially undermining the reliability of these methods in forensic analysis. Therefore, one of the essential conditions for efficient learning of these systems is the large size and diversity of a training set. Additionally, these data often require extensive processing for a more efficient classification via supervised learning. As a result, the training data must be carefully produced and maintained because biases, inaccuracies, and lack of diversity in the training set will be reflected by, that's right, bias, poor accuracy, and spurious correlations in the output. As we all know, garbage in, garbage out. A promising avenue in addressing the black box dilemma is the concept of explainable artificial intelligence. In short, this approach offers a visualization of the inner processes aiming to make the explanations as intuitive and informative as possible. This method significantly improves the explainability of predictions by ensuring AI predictions are grounded in realistic and plausible scenarios. Using vast, well-curated databases, developing more transparent and interpretable, in other words, white box algorithms, and their extensive validation can increase confidence in the results produced by these systems and ensure their acceptability in legal contexts. At the same time, it's equally important to maintain privacy and ethical standards, particularly when dealing with sensitive genetic information and personal data. Therefore, collaboration between AI developers, forensic experts, and legal professionals is essential to develop transparent, equitable, and ethically sound AI tools for forensic investigations. So let's summarize. The integration of AI and machine learning methods in forensic science represents a powerful and irreversible progression. AI's ability to integrate and analyze multidimensional forensic evidence offers a revolutionary approach to DNA mixture interpretation, pattern evidence analysis, and more. This symbiotic approach promises to enhance investigative strategies, offering new insights and interpretation of evidence. At the same time, we should be aware of the potential consequences of AI implementation, which may lead to over-reliance on the AI-dominated evaluation of evidence and even letting the AI tools reach conclusions without human experts' oversight or intervention. As artificial intelligence continues to shape the landscape of forensic science, the forensic science service providers' leadership should stay informed on these emerging tools, develop training resources, consider partnerships with academia, and plan for use cases and admissibility. And finally, I want to finish with a call for action. As we stand on the brink of this AI revolution in forensic science, let us embrace AI and machine learning not just as tools, but as allies in our quest for scientific truth and justice. Let's be the architects of this new era and actively contribute to the development of transparent, ethical AI tools, offering a beacon of hope for unsolved cases and people who were wrongly incarcerated. Thank you.
Thank you so much for this super interesting presentation. This is such an exciting topic. I have a few questions that the audience might also be curious about. So, what kind of AI-proof skills would the next generation of forensic professionals have to equip themselves with so they won't stay behind?
Yeah, thanks Chantal, and thanks for this question. It's a great question. It's very important that the next generation of forensic scientists, and I would say even the current generation, really continues their education and learns the at least the foundations of machine learning and AI to keep up with all the developments. And this area is developing so rapidly, right? As we see, so it's really important to learn the the basics of machine learning, the foundations, and make sure that we humans are remaining relevant, right, with this AI revolution, because that's something that I hear a lot from my colleagues that are kind of afraid that AI gonna just replace us very soon. And as I said in my talk, I don't really think that's going to be the case, because we still, by we, I mean humans, still have these skills like creativity, right? And experience, which I don't think AI has and will have, at least in the near future. So things like critical thinking, creativity, and obviously bioinformatics skills. These are really, really critical in these journeys. So it's really important to learn these skills to ensure that we keep up with all these developments.
Sounds good. Thanks a lot. That makes a lot of sense. Given the significant advancements in machine learning, how do you foresee its integration evolving in forensic DNA profiling, especially regarding SDR genotyping and DNA mixture analysis?
Machine learning, due to its very powerful capabilities to handle these very large data sets, very diverse data sets, I think could be very useful in very different areas, but specifically if we talk about SDRs, that's analysis of complex mixtures, right? So this area is one of the most controversial areas, I would say, in forensic DNA analysis, and especially estimating the number of contributors in those mixtures, and especially providing a statistical way to the low-level contributors, right? So machine learning methods can not only streamline this process, right, to make it easier for human analysts, but also standardize this process to make sure that different labs essentially produce the same output, right, which is very important. And on the same token, I think it's very important to make sure that these machine learning systems are validated before they can be implemented in forensic analysis. So that's one of the key issues, and to make sure that they're admissible in court. So all these results should be admissible in court, of course. And as I mentioned in my talk, these tasks requires a collaborative effort, right, of forensic professionals, academia, and legal professionals working together to make sure that indeed we moving into the right direction and taking, I would say, baby steps towards this this aim. Yeah.
So machine learning models, they can be complicated, right? And they can introduce potential bias, as you mentioned in your talk. So what steps do you believe are crucial in maintaining reliability in forensic DNA analysis?
Yeah, that's a very important question. So the reliability of analysis based on machine learning methods is essentially, as you said, based on data that we provide these systems. So it's important that this data is diverse and large enough to essentially encapsulate all the different types, all the variability in these variables, right? So, and another important thing is that these data sets must be well curated, right? So they must be updated regularly to, again, include all the new things, all the diversity. And only this way we can ensure that the output produced by these machine learning systems is reliable, right? So we need to ensure that the data that is used to train these systems is accurate, is large enough, and diverse enough. So this way we can ensure that the output would be indeed reliable and accurate.
Thanks a lot. I think this is such an important topic. It's really important. So last question. Machine learning and forensic DNA profiling offers great potential, right? As you have explained really well, but it also comes with complexities. So how do you propose that we address the challenges of integrating these sophisticated technologies into the forensic field without compromising the integrity and reliability of forensic evidence?
Thanks for these great questions, Chantal. And let me answer by just saying three things. So these systems must be reproducible, independently validated, and transparent. I think these three things are the most important to make sure that their results are accurate and approved by the legal community. as with any new tool, especially such a powerful tool, it's really important to look into the ethical side of it. First of all, at least from my perspective, I think that's the most important part, and apply these tools reliably and ethically. So it may affect some communities in very disproportional manner, and we all know all these examples. So it's really important that before we really implement these such powerful tools, we really make sure that we know their limitations, right? And we have also covered the legal side, and we know what to expect, right? So, and we know that it won't disproportionately affect people who already are, affected by the criminal legal system, by the criminal justice system. Sorry.
Thank you very much, Mark, for these great insights. There's a lot of things to think and talk about in the future. Thanks again.
Thank you so much, Chantal, for this invitation. It was my pleasure. Thank you.
With the Seq Studio Flex Genetic Analyzer and GMapper IDX software version 1.7, the number of overall edits during analysis are decreased due to the default algorithms. This includes the auto-spectral calibration on the Seq Studio Flex system and the pull-up detection in GMapper IDX software. The Seq Studio Flex uses the same dye information to continuously update the spectral information and reduce the number of pull-up peaks that could be called. GMapper IDX software then can either label or delete those pull-up peaks, reducing the number of calls even further. Analysts can then spend less time on artifacts and more time on potential contributor peaks in complex mixtures.